All right, so here we're talking about section 10.5, which is all about complex numbers. Okay, so this is kind of like polar in the aspect that it uses some of the idea from polar coordinates, but it's another technique you can use with trigonometry ideas. Okay, so let me quickly refresh some complex numbers. Hopefully, this isn't totally new. Um, but well, first off, if we start off with what's called an imaginary number, I would imagine you guys seen this before, like that I, right? So I is defined to be the square root of -1, right? I know it's always weird. People always ask, imaginary numbers. How can you have imaginary numbers? Well, they're not just imaginary, like made up for whatever they want. They're made up in a very special way, right? I mean, like negative numbers happen all the time. Square roots happen all the time. Now, in the real world, you can't take the square root of a negative, right? There is no number times itself that'll end up being a -1, for example, or any negative number. Okay, but these things need to be there, right? In order to fill in all the gaps to make all the theories work correctly. Okay, so they came up with this idea of an imaginary number. And so basically, when you see a negative underneath the square root, that's referring to the I. For example, right, the square root of -4. What number times itself would give you -4? Well, you could think of it as like the square root of 4 is the 2, and then that negative underneath the root becomes the I. So now you're dealing with this imaginary number 2I. Okay. Same thing like if you had the square root of -32. Again, you can do that same trick where you forget the negative for a minute and then reduce the 32. You know, you think of it as 16 times 2. Square root of 16 is the 4. Leave the 2 inside. It's just that the negative, when you see the negative, it comes out here. One thing you probably want to try to avoid is this, right? I mean, is this possible? Yeah, it is, but let's try to ignore that, right? So make sure when you see I, it inherently has the square root on it, right? So that I is taking the place of the square root, okay? Because if you said the square root of I, then really what you're talking about is the square root of the square root of -1, which is possible, but that's not what we're talking about, okay? So watch out for that. It'll make more sense if you haven't. I mean, I would imagine you've seen this before, but in the larger context, we'll get to this stuff. All right. So one of the biggest things you need to realize here is also why we would need this is because if I is the square root of -1, then if I took and squared it, right? If I square both sides of this equation, there's your I squared, but then the square root kills the square root, leaves you with a -1. So you can almost think of it as like, well, why do I need imaginary numbers? Well, if I ignored an imaginary number, then you've ignored this. But you've also ignored it again, so that thing you're ignoring times that thing you're ignoring, that turns out to be a real number. So if you ignored imaginaries, then eventually you would be ignoring real numbers, right? Because two imaginaries here, for example, can turn into a real number. So we need them, right, in order to make everything work correctly. Okay? All right, so now we're going to talk about this idea of a complex number. It's complicated, right? It's complex because it's got two pieces to it, two parts, right? So a complex number, call it Z. So it's one number, but it has two different pieces to it, right? They usually write it as A plus BI, or think of it as this part is the real part and this is the imaginary part, right? I mean, just quickly, we'll talk about what the heck's going on with this problem here. But you can see like 5 plus 2i, for example. It's one number, it's 5 plus 2i, but it has different components to it. The real part here is 5, and the imaginary part is 2i, right? You probably saw this, like especially when you're solving polynomial equations, right? Finding the zeros. Hopefully that's ringing a bell. Whatever, not a big deal. But it turns out this idea is probably new, I would imagine. Okay, it turns out you can. I mean, think of like a normal number line that you're used to. Like, think of a number line, and you said, okay, let's say I wanted to do like 6 on a number line, right? I mean, you say, okay, here's 0, here's 6, right? 1, 2, 3, 4, 5, and then there's 6, and then you would draw a dot at 6, right? That's a normal number line, okay? But what if I wanted to do a complex number on a number line? Well, instead of a number line, we can think of it as a complex plane. What I mean by that is, imagine you had a normal number line that would be your real axis, and then you could also have an imaginary axis, right? So you could think of it as kind of like the real part, that's a number line this way, and then, well, I guess it would be more like this. Then the imaginary axis would be its own number line, right? And that's what creates this plane. It's kind of like the usual XY plane or polar plane, whatever. It's just that instead of an X and a Y, it's now the real part and the imaginary part. Okay, so it's that usual, to plot this one number, right, in this plane or this point, if you want to think of it that way, whatever the real part is, that's how much you would move left or right on the real axis. And then whatever the B is, that's how much you would move up or down on the vertical axis, right? I mean, it's pretty easy once you get used to it, but it's just kind of new, I would imagine, right? So here, let me show you. All right, so I want to plot each complex number in the complex plane, right? So, well, here, let me just write these over here so I don't have to. Okay, so it's kind of like that usual. And we could draw a full grid if you wanted here, but it's that usual stuff where the only thing that's different is this is the real part. You've probably seen this before with the R here, and then this would be the imaginary part here, right? So, I mean, there really isn't an abbreviation for the imaginary part. Actually, there is for complex numbers. When you see a C with an extra line through it, that's the abbreviation for all complex numbers, just like this R is for all real numbers, right? Or the set of real numbers. Okay, but whatever. So, I mean, just for simplicity, let's call this A, B, C, and D, right? So it's pretty much, I mean, it's pretty easy, right? So if you can plot points, you can plot these, right? So it's 5 plus 2i, right? So the real part here is obviously the 5. So 1, 2, 3, 4, 5. And then the imaginary part is 2. So you would go up 2, right? So there's your point A, right? It's kind of like drawing on a number line. It's just that instead of going left or right, you also have an up-down component for the imaginary, right? So now the -2 for the real part, and then down for 1, 2, 3, 4 for the imaginary part, right? It's pretty simple. It's pretty straightforward, right? A couple things to watch out for. Again, not tricky, but do watch out for it. Like technically, it's like z equals 4. It's a real number, right? It's only a real number, but technically, it is a complex number as well. I mean, every single, if you think about every number on the normal number line that you're used to, is a complex number. It's just that it was missing, or think of it as it has the imaginary part of 0. Right? So actually, on a number line, there was actually the complex plane there all along. It's just that they never referred to it because you could go, for example, right 4, but then just don't go up or down because it doesn't have a imaginary component to it. Or you want to probably think of it as the imaginary component is 0, I, right? And then the other way too, you could have a complex part that has only an imaginary part. It doesn't have a real part, but then you don't go left or right, and you would just go up 6. Right? So pretty straightforward. I don't think that's too tricky. But it is kind of a new idea, the ability to actually plot a complex number, right? But left right is the imaginary, the real part, and then up down is the imaginary part. So pretty straightforward. Okay. Now it turns out we can do all kinds of things with complex numbers. Okay. So just like with regular numbers, you can talk about the absolute value. Okay. You can talk about adding them. You can talk about multiplying. We'll get to all this, right? But you can talk about adding them. You can talk about multiplying. You can talk about dividing. You can talk about roots of these things, right? So that's pretty much what we want to get to here is adding, subtracting, multiplying, dividing, roots, and absolute value. Okay. But the thing of it is here is you're talking about absolute value. Remember what absolute value is? I mean, for regular real numbers, you're probably used to it. It's pretty easy, right? I mean, everyone always says the phrase, "Oh, the absolute value is always positive." Well, no, that's not true. The absolute value is either positive or could be 0, right? But think of it as what is the absolute value? The absolute value is the raw distance from 0. Or in other words, it's how far you'd have to go to get to 0, right? Because if x were a positive number, then the absolute value of x is just how far you'd have to go to 0, but positive. And if x were a negative number, it's still how far you'd have to go to 0. You just don't care that you're walking the other direction, right? I mean, it's pretty simple. The absolute value of 6 is 6, right? The absolute value of -6 is also 6. Both of them would represent how far you would have to go to get to 0. 6 in this case. Okay. Now, what happens if you wanted to find the absolute value of a complex number? It's literally the same idea. It's just that now instead of on a number line and walking, on a number line walking just all the way to 0, right, on this horizontal, now there's also a vertical component, which means you would have to go kind of on an angle depending on what's going on, right? Because remember, you could be up here in a plane. But how would you find that? Oh, it's that usual, whatever the A is, whatever the real part is squared, plus whatever the B is, the imaginary part is squared, and then take the square root. Right? So using the Pythagorean theorem, the absolute value of a complex number is really the square root of a squared plus b squared, right? Okay. So let's check this out. So let's say I want to find the absolute value of each of the following. Okay. So for the first one, it's 1 minus 2i. It's pretty straightforward once you get used to it. So the absolute value of z would literally just be the real part, which is 1 squared plus the imaginary part, which is the -2 squared, and then take the square root. The only thing to watch out for is you're not squaring the I here, because remember, I squared is -1, so don't do that, right? That you're just using the A is 1 and the B is the -2, right? Because think of it as what you're doing is you're talking about the number on you when you plot this, right? The real part is 1, and then down here is -2, right? So this component is 1, this component is 2, it's down 2. And what we're after is basically that raw distance to 0, right? Or this would just be 1 plus 4, which is basically √5. Which you could leave like that or get the decimal, okay? Watch the directions. If it says exact, leave it, right? Remember that. Exact means don't give me approximations. If it does say approximate or round it, or if it doesn't say, it's up to you, okay? The same thing with -3 minus 4i. Basically the same idea. So in this case, you'd be taking the -3 and squaring it, and then taking the -4 and squaring it, and then taking the square root. Again, you can kind of visualize, right? Left 3, down 4, so it's over here. So what we're after is that raw distance back to the origin, right? Okay, which again, so basically this is just going to be 9 plus 16, then you take the square root, which is 5, right? Right, because this would be square root of 25, so indeed that would be a 5, right? It's the usual 3, 4, 5 triangle, okay? But hopefully you realize, I mean, whether you were here, or you were over here, or you were over here, or you were over here, right? I know this particular one is -3, -4, but whether this were positive or negative, you get the same thing. Whether this were positive or negative, you get the same thing. So you can kind of visualize those 4 points would all have the exact same, and there'd be other ones too, right? But at least they have the same, 3 being the real part and 4 being the imaginary part. And whether it's positive or negative, it doesn't matter. The absolute value would still be the same. Just like the absolute value of 6 and the absolute value of -6. It's the same. It's still the same distance to 0. Okay. And then it's probably worth checking out here as well. I mean, if z is -6, I would imagine you could just say, oh, right, that's just a real number, so what's the absolute value of it? It is +6. But do realize that if you think of it in the complex world, what we're talking about is, well, it's over here is -6. So what we're really talking about is this distance here, right? Which, again, you can just look at it as 6, or do see that you could think of this as, the real part is -6 squared, plus the imaginary part is 0. But again, that's going to turn into +6, right? Because this is going to turn it, well, let me ask you the whole thing. This is going to turn into 36, and then this is 0, and then you're taking the square root. But again, you're still back to 6, right? So whether you look at this and say, hey, this is a real number, so it's like the normal absolute value that you're used to, or you could do that. I mean, basically, the point is anytime you're taking the absolute value of a real number, you were doing this before. It's just that the imaginary part was 0, right? And then the squaring turned it positive, and then take the square root turned you back to the normal magnitude that you're used to. Okay. As a matter of fact, you could take this a step farther. It's slightly deeper than what we need here. But who's to say it wasn't a 3-dimensional deal, right? Left, right, up, down, and then what if there was the 3rd dimension coming out at you? It turns out you could do the same thing, right? You would do the left, right component squared plus the up, down component squared plus that 3rd component coming out at you squared, right? It's just that it's always been 0 before. That's why it works, right? Or whatever. If you follow me on that, great. If not, for those of you going deeper, like Calc 3, pretty much, you get in that 3-dimensional, 4-dimensional, 5-dimensional, infinitely dimensional things. And it turns out you've been doing it the whole time. It's just that all those dimensions were 0. Right? Whatever. You'll get there. Well, maybe some people. Okay. But ultimately, the point here is you got this absolute value idea, right? It's basically just the Pythagorean theorem where you're squaring the individual components individually and then adding them and then take the square root. All right. Now, ultimately, we want to talk about adding, subtracting, and multiplying and doing all this crazy stuff with complex numbers. But it turns out, right, I mean, if we have a plane here, we can also talk about the polar form of complex numbers, which is why we are talking about it in this class, right? Because it's all about, trig stuff. Okay, so it's that usual stuff. I could think of the rectangular version as the real part and the imaginary part, and then R would be basically the absolute value, right? Okay. I mean, and you're talking about polar R. I mean, like, I guess what I'm saying is, if you're talking about the actual true absolute value, the absolute value is going to be a positive number. Okay. Now, in polar, could the R be negative? Yes. Just remember, negative R just means you're walking backwards, right? So I should watch that. R is not necessarily the absolute value. It's the same size as the absolute value, but R could be negative, meaning you walk backwards. Or whatever. It's basically the same premise. Okay, and then the usual stuff. You can talk about cosine is a over r, or the real part you can write as the r cosine of whatever the angle is, and then the same thing with the sine. The imaginary part b would be r sine theta, and this is true. Tangent theta is b over a, but it's really not all that helpful in our context. Okay, so it turns out you can take the rectangular version, right, of a complex number that has a real part and imaginary part. I can turn a into r cosine theta, and you can turn b into r sine theta, right? And since both of those have an r, you can factor it out, right? So you can think of it as the raw distance you're walking times the quantity of cosine of the angle plus I sine of the angle. Now this r is times the whole thing, okay? Now, here's the beauty of math people are lazy, right? So they came up with this new notation, the cis notation they call it. So this is r cis theta. Now, you don't want to abuse this either. So this is r times cis theta. But what is cis theta coming from? It's cosine, right? The C is for cosine of theta plus I sine of theta. So I mean, this is the lazy way of saying you're whenever you see this theta here, you're taking the cosine of that angle. You're also taking the sine of the angle. The cosine of the angle is kind of like the real part with the r, and the sine theta is kind of like the imaginary part with the r, right? It's just that this is just a lazy way of writing it. It turns out, why would you want to do this? Because it makes computations later on way faster, even faster than rectangular. You'll see. Okay, so let's check this out. So, whatever. So for example, 3 here, let's say I wanted to plot this in the complex plane and then write it in polar form. Okay, so you can think of this as -3, right? That's my real part is -3, and the imaginary part is also -3. So you're going left 3, down 3, right? So that's the usual left 3, down 3. Okay. Now I can talk about it in polar form. Okay. So how do I get there in polar form? Think of it as I need to start, usually in the polar axis here, and you're going to rotate around until I get to this and then walk out towards it, right? Okay. So I got to find that angle there, right? Okay, so how do you find that angle there? You could kind of play around with, the numbers on this, or you can, I don't know, that's one you might want to just know. I don't know, maybe not. But I guess first thing you could do is figure out what the R is. So the R is kind of like the absolute value, right? Or think of it maybe as R squared is going to be the -3 squared plus the -3 squared, right? So this is going to be 9 plus 9, which would be 18, right? So R squared would be 18. So then R would be the square root of 18. Now, technically, this would be plus or minus square root of 18, which you could leave like that, or you could think of this as 9 times 2, the square root of 9 would come out. This would be 3 root 2, which, I don't know, maybe just me ever doing this long, but if you think about it, you could have just jumped from that, right? Because this is 9, which means you have 2 of them. So since the square root of 9 is nice, you could have left that as the 3, and since there was 2 of them, that 2 would remain inside the root. Whatever, you'll still get there. Okay, so one thing is, when you're talking about polar, again, R could be positive or could be negative. So you could either turn this way and then walk forward using a positive R, or you could use this angle and rotate down and then use the positive R and walk forward. Or you could turn this way and face the opposite direction and then use a negative R. Or heck, I don't know why, but you could use a negative angle where you rotate all the way around to here and then walk backwards R with a negative R. Again, you got options. Okay, most of the time, the most ones that people like to use is use a positive R and a positive angle theta, right? I mean, this is what you're used to, is rotating this way and then walking forward. That'll work. But if you do that, I mean, like, you can play around with it, but okay, think about that. The x coordinate, right, the real part, and the y coordinate, the imaginary part, are exactly the same. That's only going to happen at 45 degrees. Okay. Worst case scenario, if you don't see that, you could use one of these relationships, since we know what these are. You could even use this one if you like, right? But think about that. You could do something like the tangent of the theta there would be -3 over -3, but that's 1. Oh, right? That means my reference angle would indeed be 45 degrees. Again, you could use 45 degrees, but then you better walk backwards, right? So maybe I should write that. So what I'm saying is you could use 45 degrees. Okay, so you could write this as cis 45 degrees, but then your R, you would use the 3 root 2, but you would need to walk backwards. Okay, or you could use the positive 3 root 2, But then instead of 45 degrees, you would have to go all the way around here. So 180, more than 45. So 225. Right? So either one of those would work. Okay. Now, one thing I do want to mention is, if you're going to use this one for example, I mean, either one would work. But what this really means, remember, is it's really 3 root 2 times all of cosine of 225 degrees plus I times sine of 225 degrees. Right? So it's that whole thing. This is just a lazy way of writing it, right? This is just the notation for it, right? Unfortunately, if you check this out on the calculator, there is no, well, depending on which calculator you have, most of them do not have a sys. They do have cosine and sine, right? So you can do that as a check, right? Oh, I should mention, the I is usually on the decimal point, right? See, it's yellow, or the I, so you can use that. So, oh, and then also the angle here, you could use radians or degrees. I know most of you guys like degrees, so you can always use degrees if you like for this, whatever, right? It's up to you, okay? So what I'm saying is, as a check, right, you could do 3 root 2, close that, and then open parenthesis for the whole thing. So cosine of 225, close for that, plus, then call up that second I, right? So it's cosine plus I sine of the 225, right? And then you probably should close that for the whole parentheses. Actually, you don't really need to, but whatever. And there you go. See, look, it's the same thing. The negative 3 minus 3i. And it'll, I mean, like the calculator will always display in A plus BI. It'll always display it in rectangular format. It will never display it in polar. Okay, but it does work. Okay, at least being able to plug it in there. All right, so that's going one way, and then you should also be able to go the other way. What I mean by that is, let's say I gave you in polar form and you want to convert it to rectangular form. Now, one thing you probably should be able to plot what this looks like first and then convert it to rectangular and confirm that, hey, you're probably in the right spot. So I'm talking about 5 cis 30 degrees. Okay, just writing it down. All right, so what does this look like? So what this is saying is, starting usual stuff, polar axis here, I'm going to rotate 30 degrees and then walk out 5, right? So imagine going up here and walking out 1, 2, 3, 4, 5. And there's my point where you rotated 30 degrees. Okay, so now what does this truly mean? Again, what this means is 5 times all of cosine 30 degrees plus I times the sine of 30 degrees, right? Think of it as almost like you're taking this 30 degrees and you're distributing it to the cosine, and you're also distributing it with the sine, right? And then the imaginary part is always the sine part, right? Because remember, that's the vertical. And then you can just plug and chug from here, right? So cosine of 30 degrees, right? 30 degrees, that's a smaller angle, right? So cosine would be longer, so that's the root 3 over 2, plus I sine would be the 1/2 then. And there you go, right? I mean, like I said, you could leave it like that, or to make it look like the standard A plus BI format, you could distribute the 5. So you could think of this as the 5 root 3 over 2, plus, if you like, the 5/2 I, just so that it looks like the usual A plus BI, right? So the 5 root 3 over 2, that's the real part, and the 5/2 is the imaginary part, right? Which, again, this is not a pretty number, so it's not going to look very nice on the calculator, but you could check that. Like, what I mean by that is type the whole thing in. So 5 parentheses cosine of 30 close plus the I sine of 30 close, right? So cosine of 30 plus I sine of 30 times the 5. Now, see, the problem here is it's going to give you, whoa, crazy decimal, plus, then you can see the 2.5 I, right? Well, the 2.5 I, that's pretty obvious, right? There's your 5 over 2. And then you could check, if you wanted to, the 5 root 3 divided by 2. That is indeed that same 4.3333, right? So that is the real part, and then the, obviously the 5/2 is the 2.5 for the imaginary part, right? Okay, so step 1, being able to convert back and forth from polar to rectangular. Okay. All right, so now that we have a rough idea of, and we'll do a lot more of this, don't worry, it's not going away, right? But of converting back and forth between the rectangular and then the polar form, and then the polar form to rectangular form, so back and forth. Now, we want to use these, right? What I mean by that is, again, we want to find the product of these, right? Meaning multiplying, dividing, all this good stuff, okay? So, honestly, we want to be able to do it in both, but you'll see the rationale here why polar form is so nice, especially when you want to look at the product of these things, right? So Let's in rectangular form. Let's say you were given two different, imagine or complex numbers in rectangular form, right? So let's say the first number here, z1, is a1 plus b1i, and z2 is a2 plus b2i. I know there's a lot of crazy notation, but don't get lost, right? So this is just the subscripts are just so you don't get the numbers confused between which one's which, right? So this first a complex number has the first real part and it has its own imaginary part. The other complex number has its real part and its imaginary part. Okay, so now imagine you wanted to multiply these together. How would you do that? You would take the one number multiplied by the other number, and when you write it out like this, it's hopefully just screaming at you, oh, I'm adding two things here, adding two things. You'd have to FOIL it all out, right? So when you FOIL it all out, keep in mind that I squared, right? When you do that, the imaginary part times this imaginary part, you're going to end up with an I squared, which is -1. Okay, so let me show you what I mean by this before we get to the polar form. So let's check out example 5 here. So I want to multiply the complex numbers 3 minus 4i and -1 plus 2i. Okay, and it did want me to leave it in rectangular form, right? So I don't know where you guys are coming from, but I would imagine this part is probably not new, right? Just multiplying this out, right, in the usual rectangular form, right? So you got to FOIL it all out, right? So the 3 times -1 would be -3. 3 times the 2i would be the 6i. And then the -4i times -1 would be a +4i. And then here, the way I would do this is kind of through 3 different steps. Like, first worry about the sign, right? The negative times the positive, it's going to be a negative. 4 times 2 is going to be 8. And the I times I is going to be I squared. But keep in mind, this I squared is really -1, which means you really have a +8 here, right? So that, which is ultimately why we need this stuff, is because imaginary can turn into a real number, right? That's why we can't ignore imaginary numbers. Okay, because now you can add up like terms, right? So the -3 plus 8, these are the real parts. We can add these together, which just leave you with the 5. And then the imaginary part that stays imaginary, you can add together. 6 of them, 4 of them is 10i. And there you go. Okay, and then it's the usual a plus bi format. Okay, now I know this is crazy. Whoa, look at all this stuff. Okay, wait. The punchline is incredibly nice. Just bear with me. You don't have to watch this one time, okay? But imagine you wanted to multiply two numbers in polar form. Okay, so what's that going to look like? One number is going to have an r and it's going to have an angle. The other number is going to have an r and an angle. Okay, well, remember what that cis means. What it really means is cosine of the angle plus I times the sine of the angle. Okay, and that's the same thing with the second number. It's cosine of the angle plus I sine of the angle, right? So this is in polar form. This is one number, and this is the other number. Okay. Now, since it's multiplication, I can just put the numbers out front, the r's out front. So r1 and r2 I can throw out front. Okay. And then this and this, right? It's kind of got the two terms, right? So you have to FOIL it out. So you got to do the cosine of theta 1 times cosine of theta 2. Okay. Now you might say, oh, isn't that just cosine squared? No, because they might be different angles. If these were the same angle, then yes, this would be cosine squared. But they could be different angles, which means you'd have to leave it together. Then the cosine theta 1 times I sine theta 2. And then the I sine theta 1 times cosine theta 2. And then the I sine theta 1 times I sine theta 2. Again, the I times I is I squared. And you got the sine theta 1 sine theta 2. Okay. Now, again, you could do that same kind of trick where see, like, this is I squared is going to turn into -1. So this is a regular real number part, right? And this would then turn into the real part. Then this part is imaginary and this part is imaginary. So since this and this are imaginary, you can factor out that I, and that's what's leaving you with these parts here. So all of this is the real part and all of this is the imaginary part. Now, you'd have to go back, but this should kind of look familiar, right? Cosine of an angle minus sine of the same angle, sine of the second angle. Oh, that's that cosine of two different angles being added together formula, right? That's the sum formula. And the same thing that happens here. Sine of an angle, cosine, and then it switches. Sine of this one switches here. Oh, that's the formula for the sum of the two angles in the sine. So now we're right back to some number times cosine of an angle plus I sine of the same angle, which now we can write that back in that cis format. Which basically, what is the punchline here? The punchline is, if you have it in polar form, what does it turn out to be? You literally just multiply the r's out front and you add the angles. Done. You don't have to multiply it out anymore. I mean, you're multiplying it out, yes, but you don't have to FOIL it out anymore, right? The shortcut is basically you just multiply the r's and add the angles. Done. Okay, but that's the nice part about you, because we have those crazy formulas, right? They're crazy formulas, but they do turn out to be nice in the end. Okay, so let's do this. So with example 6, let me just write these down. Hold on. Okay, so I just want to find that product. And it even says leave in polar form, which honestly should take less time to write the answer than it would to do any thought process. I mean, and that's the beauty of these things, right? I mean, because the beauty of this is, okay, so then what is the multiplication of it? You literally multiply the r's together, 28, add the angles together, 25 degrees, right? 25 degrees plus 15 degrees, 40 degrees. I'm done. Right? I mean, seriously, it doesn't get any easier than that. That's the point, right? Which is crazy, right? To think about that, right? If you take this crazy number here, this number here, and multiply them together, that's what it is. Now, you could go and switch it to rectangular form if you would like, that would work. Or heck, you could, it's a lot of work, but you could type this whole thing in the calculator, multiply by this whole thing in the calculator, and then type this in the calculator, right? And then see that it does indeed give you the same. Right? But the point there is if you stay in the polar world, it doesn't get any easier. Even if you had some crazier ones like this. So let's say you wanted to do these two here, where you wanted to do the 3 cis 5 pi over 8, and you want to multiply that by 10 cis pi over 16. One thing you got to watch out for is, the cis tends to look like cosine by itself, so you got to watch that, because that's a huge difference, right? We're not talking about just cosine, we're talking about cosine of this angle plus I times the sine of this angle, right? So there's a lot happening here, but it's still pretty easy, right? Because you can multiply and add, right? So literally this would just be 30 cis. That's a little trick here, right? But maybe you got to come off to the side and say, oh, Ray, what am I doing? I'm doing 5 pi over 8, and I'm adding pi over 16, right? So in order to add those, you would need a common denominator. So you have to multiply this one by 2. So this would really be 10 pi over 8, not 16, and then pi over 16, right? Just multiply down bottom by 2 to get a common denominator. So then ultimately this would be 11 pi over 16. Right? So even if it's in radians, it still works. Okay. So I mean, literally, it's just multiply, add the angles, done. Pretty simple. Okay. It might be worth doing it just once. I know this would be crazy annoying, but just bear with me. What I mean by that is, you could convert this, to polar, convert this to polar, use that same idea, and then convert back. Right? I mean, I know this isn't all that bad, right? I mean, multiply this out, but just to show you that it does work. Right, this is just a study in how these things work, not necessarily like this is better. So what I'm saying is, let's say I wanted to convert this to polar. So 3 minus 4i, right? So you're going right 3, down 4. Okay, so we need an angle here. Now, again, you could, for simplicity, rotate down. So then the angle here would be, you can use the inverse tangent, right? Because remember, you went down 4, and you went right 3, right? So you could use the inverse tangent of negative 4/3. And then your r would be the 3 squared plus basically the 4 squared, right? Because when you square the negative, it's going to turn positive anyway. But if you rotate down, you're already facing the right way, so you can just use the positive version of this, right? Which hopefully 3, 4, 5, that's right. Right? But you could go through the 9 plus 16 is 25, square root of 25 is 5, right? So you could use that. But now the problem here is the tangent inverse of negative 4/3. Whoops. It's not going to be a pretty number. So the problem with this is now you're going to be approximating. So when you use that, is it going to give you this exact answer? No, but it's going to get you close, right? So what I mean by that is you could use the angle. Well, I guess I already have it here. So you could use that angle of negative 53.13 degrees. Okay. Or since you already have it there, just store it to your x if you would like. That way you can use the whole thing, right? You can use that store feature if you like. Whatever. That's up to you. Okay. But what I'm saying is you could write this ultimately as 5 cis negative 53.13 degrees. Okay, and then do the same thing with the other one, negative 1 plus 2i. So negative 1 plus 2i. So here you're talking about left 1, then up 2. Okay, so then your angle here would be, you could use the inverse tangent of, so it's up 2, left 1. So it's basically 2 over negative 1. Okay, So if you're going to do that inverse tangent of, well, basically -2, right? It's 2 divided by -1. Now, if you use a calculator, it gives you -63.43. Again, you can use that, but remember that is coming down here, okay? You would just have to walk backwards. So you either add 180 to face it, or you could use the negative version of r, okay? So you could think of this as r squared would be the -1 squared plus the 2 squared. So then r squared would basically be, well, do the whole thing, 5, right? 1 plus 4 is 5. So you could use a -√5 for r, right? That way, you can leave this angle and just walk backwards, okay? So you can think of this as a -√5 cis -63.43 degrees, okay? So the point that I'm making here is if you were to take the 3 minus 4i and multiply by -1 plus 2i, right? Instead of doing it rectangular, you can convert this to polar, which was the, 5 cis -53.13 degrees, okay? And you're going to multiply that by the other one here that we did, which was the -√5 cis -63.43 degrees. Sorry, I ran over there. Okay, but now that we have it this way, how could you do that? Think of it as, here's your r part, and then here's the angle part, right? So you literally just multiply the r's together, which would just be the -5√5 cis. Then you could add these together, which, to get a better, when you do this, it's this one plus the thing that we stored for x, right? So when you add those together, roughly you're going to get -116.57 degrees, okay? Which I could now take and store that to x, okay? So now, basically, there's my answer, okay? But it's in polar form. Now, you could take the -5√5, right? And then in parentheses do the cosine of that angle that we, because we just stored that to x at -116, plus I sine of that angle, okay? And see, you end up with 5 plus 10i, which is exactly the same thing that we got doing it the rectangular way, okay? Again, is that faster? No, of course not. But the point is, it works, okay? That's the point, okay? So depending on the numbers, one way might be better than the other, okay? But it works. Okay, so multiplying turns out pretty nice, right? You just add multiply the r's and then add the angles. Okay, what if I wanted to do the quotient? Okay, meaning I wanted to divide two complex numbers. Okay, in rectangular form, I want to take one number divided by the other number. Okay, which I don't know, you may not have, usually depending on where you came from, calculus or whatever, they probably didn't do a whole lot with this. Okay, because the reason why is because in rectangular form it's really nasty. In polar form it's really easy. I'm not going to go through the proof for it because I think it's pretty straightforward. You can check it out, but take a wild guess, right? If in polar form, if you're multiplying, you multiply the r's and you add the angles, it's exactly what you would think here. You divide the r's and then just subtract the angles when you're dividing, right? So it's literally you divide the r's and subtract the angles instead of multiplying and adding. Okay, but if you're in the rectangular form, if you remember, that's when you'd have to use the conjugate, which is kind of nasty, but it is what it is, right? So let me show you. That's it. So just to see it both ways. So let's say I wanted to do, with this example, I want to do 1 minus 2i, right? I'm going to take this and divide by 3 plus 4i, right? So I'm taking a complex number and dividing by another complex number. But how you do this is you multiply by the conjugate, right? Remember, so the conjugate, if you remember, think of it as the real part is exactly the same, but the imaginary part is the exact opposite. So really, I should step back because whatever. This is the conjugate, right? So what I mean by that is, if you're talking about an a2 plus b2i, right? So an a plus bi, the conjugate is the same real part but opposite imaginary parts, right? So this is the actual conjugate. It's just that if you multiply the bottom by the conjugate, you better multiply the top by the conjugate as well, right? You're really multiplying by one in a special way, right? Because the reason why we do this is because now you got to FOIL the bottom out, but 3 times 3 is 9. 3 times -4 is -12i. And then 4i times 3 would be a positive 12i. And then the 4i times negative 4 would be a negative 16i squared, right? And I still got to do the top. We'll come back and do that. But the reason why you use conjugate is especially here because you can see, oh, look, these i's go away. And again, this is going to be negative 1, which means this really turns into a positive 16, which means the bottom is really only 25. And that's why the conjugate works the way it does, because it basically turns the denominator to not have any more i's, right? So by multiplying by the conjugate, the two, because they're exactly the same, right, but opposite sign, then these two are going to cancel every time. And then that I times I, that I squared, will again turn into a real because it turns into negative 1. Okay, so the only thing left is whatever the heck the top is. But you got to follow that out too. So 1 times 3 is 3, right? Then you got the minus 4i. Then you got distribute here be the minus 6i plus 8i squared, right? So 1 times 3, 1 times the negative 4, then the negative 2i times 3, and then the negative 2i times negative 4i. Okay, so again, this is going to turn into plus 8, right? Because that, what am I doing? It's already a plus. I squared is going to be a negative, so it's going to turn into a negative 8, right? Which means the 3 minus 8, real number wise, would be the negative 5, and then the imaginary negative 4i minus 6i would be a negative 10i. Which you could leave like that, but to put it in the stereotypical format, then you could take and distribute this 25, right? So the real part here is like negative 5 over 25, or negative 1/5, minus then the 10 over 25 and cancel off of 5 would be the 2/5 I. Now it's in that standard A plus B I format. Okay, and so that's how you do it in rectangular. Okay, but in polar, it's actually easier if you ask me, right? So let's example 8 here. I'm just writing it down. Hold on. Okay, I just wrote it down. So the two numbers, right? So what I want to do is I want to take this 50 cis 80 degrees and this 10 cis 20 degrees and actually do the division. Okay. So again, it's pretty straightforward. You literally divide them and then subtract the powers. The only thing you do have to kind of watch out for is remember when you're talking about multiplying, right? Remember you multiply them, multiply the r's, and you add the angles. Well, it doesn't matter the order that you multiply here, and it doesn't matter the order you add these. You're going to get the same thing every time. Now, when you're dividing things, the order does matter, right? So make sure that whichever one you're talking about first, right? See the way it's worded here, Z1 is first. That R better be on the top. And then when you go to subtract the angles, this one better be the 80 minus 20, for example, right? So the order in which you do subtract them, in the order in which you divide the R's, does matter, okay? So what I mean by that is you probably want to think of this as 50 divided by 10, then it's going to be the cis 80 degrees minus 20 degrees, right? So divide out the R's in the same order, cis, and then subtract the angles in that order. But that's pretty easy. This is just 5 cis 60 degrees. Which I don't know, maybe it's just me, but 60 degrees, that's screaming switching to rectangular, right? Because the 60 degrees is a nice one. We know what the cosine of 60 is. We know what the sine of 60 is, right? So this one would be relatively quick and painless. Well, at this stage, hopefully relatively painless to switch to rectangle. It didn't ask for it, so whatever. Okay. The same thing with the second one, but literally the same thing. It just happens to be in radians, right? So it's the same 2 cis pi over 5 divided by the 6 cis pi over 16. And so the point here with this one is watch the radians and then also watch the way it's written. What I mean by that is don't just divide it any way you want. Since it said this one divided by this one, you have to keep that order, right? So it's not 3, it's 1/3, right? So this is going to be 2 6 cis, and then when you subtract these, this is going to be pi over 5 minus pi over 16. Really? Okay. Whatever, because this is going to be 3 cis, then whatever the heck this is, right? So you got to come up with the side. Now they both have a pi, so to make the numbers easier here, let's think about 1 over 5 minus 1 over 16, right? So the common denominator here, pretty much you're going to have to multiply those together. So whatever 5 times 16 is, or 80. So going to multiply top and bottom here by 16, top and bottom here by 5, over that common denominator of 80, right? So it's basically going to be 11 pi over 80, right? I mean, again, you could use a calculator on that if you wanted. I mean, not the pi. I mean, the pi part is just going to stay there, but you can just throw that in later. What I mean is, 1/5 minus 1/16, 1/16. right? And then just hit math, enter, and it'll turn into a fraction for you, and then just throw in your pi, right? So there you go. Again, not a nice one, right? So you probably don't want to switch that to rectangle because it's not a very pretty one, but you could if you wanted. Didn't ask for it, okay? But so far, so good, right? It's pretty simple for the most part, right? You just dividing in polar, you just divide the r's and then subtract the angles, okay? What if you wanted to do powers of complex numbers, right? So for example, you wanted to raise something to the 5th power or to the 3rd power, okay? Well, what does raising to a power means? It means repeated multiplication, right? So imagine in rectangular form, how would you do that? In rectangular form, you would take that whole thing, whatever it is, and multiply by itself that many times. So imagine for a second, how would you do this in rectangular form, for example? So 1 minus I to the 5th would be 1 minus I times itself 5 times, right? So it's 1 minus I, times 1 minus I, times 1 minus I. And I don't even know what I'm on. It's on 5 times, which means that is a lot of foiling. So this is one where, whoa, it might not be very useful to actually leave it in rectangular, okay? But it turns out in polar form, think about that. Go back to what we were doing before. If you're multiplying things, remember what do? You multiply the r's and you add the angles. So if you're talking about powers, you're talking about doing multiplication over and over and over and over and over again, right? So you would just keep multiplying all the r's, but they're all the same. So you're basically just raising that to a power. And then you would just keep adding the angles, but they're all the same. So keep adding up the same angle over and over and over again, right? I mean, I probably should have put that on there, but one thing that you might want to think of that as is, okay, let's do this. Right? You can think of this as what I'm talking about is this is r cis theta, right? And then you're multiplying by another r cis theta, and then you're going to multiply by another r cis theta, blah, blah, blah. And you keep doing this. So my point is if you're multiplying these two together, oh, then this would just be r squared. And then I multiply by the next one, it would be r cubed. And multiply by the next one, right? So whatever the r is, you would just keep multiplying by it itself over and over again. Then the thetas, you would be, okay, theta plus theta, but that's 2 theta. And then you add the next one, would be 3 theta. And you add the next one, would be 4 theta. So you would just keep adding theta plus theta plus theta plus theta plus theta plus theta, or repeatedly adding theta n times would just be n theta. Also, I don't know, I'm not a huge fan of names, but this is the fancy name for this. This is what's called the Maury's theorem, right? So if you hear that phrase in the you do the homework, because the homework does use that phrase, this is what they're talking about. But even if you didn't know the name of that, you could still probably figure it out from the homework. But this is the Maury's theorem, which I don't know why it gets in a fancy name, because it's pretty relatively easy to think about. So basically, what is the punchline here? If you want to take a polar form of something to a power, you just take the r and raise it to the power, and you take the angle and you multiply by whatever the power is. Okay, so let's do it. So here, I would imagine that's 10 degrees, whatever. Or maybe it's radians. It probably is radians, but it doesn't matter. Even if it was degrees, it's still the same idea. Okay. I mean, I can't imagine I would put a 10 there, right, for radians. I mean, it's possible, but what is that? That means you're rotating, around more than once, right? Because 2 pi is like 6 something. So maybe it's 10 radians, but I would imagine it was just typo and I meant degrees. But whatever. So 2 cis, let's pretend it said degrees. Okay, the idea is the same. But I want to raise it to the 3rd power. So again, you could sit there and write it out 3 times, but the short version is literally going to be 2 raised to the 3rd power, and then cis 3 of those 10s, right? I mean, maybe we probably should write it out so you can see what's happening here. So it's really this 3 times. No. But you can see, oh, look, if you're multiplying things, you would just multiply the r's together. There's your 2 cubed. And then you would add the angles, but 10 plus 10 plus 10 is the same as 3 times 10. Or you're basically left with 8, 2 cubed, right? 2, 4, 8, cis 30 degrees. Done. It didn't say which format to leave it in, but, you could leave it in that format. Or just to kind of play around to see what's happening here, and also as a check, you could, because again, it's 30 degrees, that's screaming, oh, let's switch that to polar, right? Because this would be cosine of 30 degrees. I switch it from polar to rectangular. Cosine 30 degrees plus I sine 30 degrees. So this would be cosine of 30 degrees, right? So 30 degrees, that's a shorter one, so cosine is longer, root 3 over 2 plus then the I sine 30 degrees would be 1/2. So if we distributed the 8 here, this would then be 4 root 3 plus the 4I. Right, so this would be the rectangular version of it. Now, I mean, again, you could, it didn't say, make sure you follow the directions for sure, but since it didn't specify, it doesn't matter. But I'm just doing this as a check, so you see what I'm talking about. So what I mean by this is you could, do this way. So if I did it's a lot of typing. Well, one thing to avoid some of that typing, what you could do is just type the number in. So it's 2 parentheses cosine of 10 degrees, right? Plus I sine 10 degrees. Close for the sign, close for the whole thing, so that it's all times that R. Watch that. Okay, so that's the number, but in polar. I mean, damn it, it's already polar. That's the number, but it's in rectangular form. Okay, now you want to raise that to the third power. Okay, so I take that answer raised to the third power. But you can see there's the real part plus the 4I. So the 4I definitely agrees, and then it's a check. You could just check out 4 root 3 does indeed give me that same real part. So I have the right answer, right? Okay, so here is the real beauty of this. And this is ultimately why we really talk about this. It's kind of our build up of this. So imagine 1 minus I to the 5th, or some other, crazy complex number in rectangular form raised to some crazy high power. In rectangular form, this means you'd have to do 1 minus I five times, right? So we'd have to FOIL this all out, get an answer, multiply by this one, simplify that, multiply this all out, simplify that, multiply this all out, simplify that. Doable, but I think what's more likely to happen there than, I mean, understanding, I don't think it's that deep, but it's so easy, and what likely is to happen there is you're going to make a silly mistake because, there's so much happening there, okay? But what I could do is, first off, let's convert 1 minus I to polar first, right? So visualize 1 minus I. What does that look like? The real part's 1, and the imaginary part is down 1, right? So we're talking about this here, right? So again, you can think of it as like 1 here and 1 here. These are the same. The only way that's going to happen is at 45 degrees, right? So you could use that angle of 45 degrees. But if you use 45 degrees, you had to go down, which means you'd have to do negative 45 degrees, right? Or you could rotate the other way and then walk backwards. It's up to you, okay? And then remember, your R would be the 1 squared plus the 1 squared. Right, and if you're going to use negative 45, right, you're rotating down. You're already facing the right way, so that's fine, right? So you just use the positive version of this, or this would basically be root 2, right? 1 squared is 1, 1 squared is 1, so it's 2, so it's root 2. So basically, your number that we're talking about here is R cis theta. And what you might want to do before you do any farther with this is check it, right? So what I mean by that is you could type in the root 2, close it, open the parentheses, cosine of negative 45 plus the I sine of negative 45, right? So there's your R times all of, cosine of negative 45 plus I sine negative 45, okay? And sure enough, it is the 1 minus I, right? Okay, so check, we're good to go. So now what I want to do is I want to do root 2 cis negative 45. Or we want to raise it to the 5th power. And here's the beauty of this, because this is way easier to do. What is this going to be? It's going to be the same thing. But remember, you just think of it as, tell anybody I said this all tonight, but you can almost kind of like think of you're distributing this, but in a very, very special way, right? So it's this root 2 raised to the 5th, and then you're going to take the angle and multiply by that, right? So this is really going to be root 2 to the 5th, cis 5 times negative 45 degrees, okay? One thing that might help is if you remember root 2 is the same as 2 to the 1/2, right? Because the square root is the same as a 1/2 power, right? Whatever the index is, that's the denominator. So really what this is 2 raised to the 5 halves, right? Which you could leave like that. I don't really care. But if you wanted to, you could simplify that, because remember 5 halves is the same as 2.5, right? Which means what you really have here is 2 whole 2s, or 2 squared, then another 2 to the 1/2. Or in other words, you really have 4 root 2, right? Or again, you can maybe visualize root 2, 1, 2, 3, 4, 5 of them, right? Here's 2, there's 4 root 2. right? So either way you want to look at it, right? So I mean, if you have 5 of those root 2s, every time you come across 2 of them, it's going to create a 2, right? But you're left with that other odd one there. Right? Or you can do this, whatever. Or heck, even if you left it like that, I don't really care, okay? Because you're going to see in a minute, it's not going to matter anyway. But it might be easier to work with if we had this, okay? But now what I want to do is really, this is going to be the angle part. I need 5 times negative 45, right? Or you take the 5 times 45, so the negative 225. And then let me do this here. Okay, so what are we talking about? This is really cosine of negative 225 degrees plus the I sine of negative 225 degrees, right? Or in other words, now we can switch this back to rectangular. So I want cosine of negative 225. Well, one thing you could do is you could think of it as, if this is negative 45, I want to do 5 times that, right? So just rotate it around 5 times, right? Or, 5 times bigger than itself, okay? Or think of negative 225. What you're doing is you're rotating down 180 and then 45 more, which would be here, right? So, because remember, you got to know what quadrant you're in. So negative 225 would put me in quadrant 3, okay? But my reference angle is still going to be 45, right? Because it's 45 more than 180. Okay, so the cosine of 45 degrees is the root 2 over 2, plus then the I sine of 45 degrees, again, is root 2 over 2. Okay, well, I have to put a bracket. But since it's negative 225, you're back here in quadrant 2, which means you went to the left, cosine would be negative, and you went up, sine would be positive. Okay, now we can distribute this 4 root 2. All right, so the first one here, let's see if we can just do it. Right, so what I'm saying here is the 4 divided by the 2 is going to be the 2, and the root 2 times root 2 is just going to turn in, well, maybe I should write this. So think of this 4 and this 2 are regular numbers, right? We got the root 2, and we got the root 2, and then we got the negative, right? So this ultimately, root 2 times root 2 is going to be 2. So it cancels this 2, so you're just left with a negative 4. And then this one here, let's leave the I there. You got the 4 root 2 times this root 2 over 2. So you got the 4 again, you got the 2, you got the root 2, you got the root 2, right? You got the 4, you got the 2 in the denominator, and you got the root 2s, okay? So again, this is going to be, root 2 times root 2 is just 2, cancels that 2, so you're left with the 4. So you're literally just left with the 4i. Right? So it's a lot of work per se in the aspect of converting it to polar, right? Using the shortcut of how to actually do powers is this, and then just convert it back to rectangular. Okay. Now, I know you're saying, why would I do all this? Because I can do it on the calculator. But you got to know what the calculator's doing, right? Because if you did 1 minus I and then raise it to the 5th power, it'll actually do the whole thing, right? Negative 4 plus 4i, right? It'll actually do it, okay? But what is it actually doing to compute that? Well, not this either, but whatever. This is would be probably the quickest way to do it by hand, at least, right? At least it avoids having to multiply all those out, okay? All right, so we can now multiply, divide them, and then powers. Okay, the last one here, which in terms of the grand scheme of using it elsewhere, is probably the most useful, but it's also the trickiest one. Okay, let me preface what I'm saying by that. Forget this for a minute. Just look at the ultimate goal here is this. You've probably seen this before. Guarantee you've seen this before. Not in this way, and you probably didn't solve these exact problems, but forget everything we've done in this, just this. What I'm saying is find all solutions, all solving equations. We've done equations all the time. Now, again, everybody's coming from different spots, what you're seeing, what you haven't seen. But if you do remember, hopefully, college algebra, solving polynomial equations. Remember, like creating that whole P over Q list, then you pick one, you do the whole synthetic division to see where you have the zeros, right? We're not doing that, don't worry, but you could, okay? But one thing hopefully you do remember is whatever the highest power is or whatever the degree is, that's how many solutions there should be, right? So what I mean by that is when you see something like x to the 6th floating around, the highest power is 6. So what that means is there should be 6 different solutions. How do we find all 6 of those? Okay, your college algebra days, you could find the real ones, and you could use some techniques if you went from college algebra to find some of the imaginary ones, but you couldn't find all of them, right? We need something new. The same thing here, right? I mean, there should be 4 of them. You can find some of them, but actually this one you can solve completely by college algebra ways, but this one you couldn't. But anyway, the point is now we can use these new ideas to help us find solutions that you wouldn't have known were there. Okay, so what we're talking about is basically roots of complex numbers. Okay, for example, let's step back. So if I gave you something like x squared equals 4, right? At this stage, you could all tell me, hey, that's going to be plus or minus 2, right? But the reason why it's 2 is because when you take the square root of 4, it could be 2. 2 times 2 is 4, but also it could be the negative version because negative 2 times negative 2 is 4, right? So there are 2 of them. Okay, so that rationale, if I gave you x cubed equals 8, you could take the cube root of both sides. So what's the cube root of 8? All right, so what number times itself is 8? Oh, 2 works, right? 2 times 2 times 2 is 8. So 2 is the solution. But wait a minute, we're talking about a cube root. So if a square root really had 2 different versions to it, right, the positive version and the negative version, then the cube root should also have 3 answers. Not necessarily positive or negative, it's not that easy, right? Evens work that way, but not odds. Anyway, but the point there is like I was talking about. If you're talking about a 6th root, there better be 6 of them. If you're talking about a 4th root, there better be 4 of them, right? So there better be 3 of them. Where are the other 2? Okay, so how you need to, well, not the only way, but once you get used to it, the easiest way is you want to find the complex roots in polar form. Okay, now there's a formula for this, but you probably want to, there's an easier way to look at this. Okay, and how this process works, right? Think of it as what you're going to do is you want to convert whatever your number you're talking about, convert it to polar. Okay, think about what the root that you're looking for of the r is. Think of it as your starting value and then the pieces, and you want to fill in the whole unit circle. So let me just show you. It's probably easier than trying to explain it in this general format. Okay, so for example, 10 here. I want to find all 3 cube roots of 8. Or in other words, we're trying to find what are all the numbers when I cube it would indeed give me 8. 2 is the obvious one, right? Because in the real world, if you use this symbol root here, the cube root of 8 is 2. Okay, so that's kind of like your r, okay, that you would use for your answer. Okay, but now again, don't get lost in this crazy notation. But think of it as we're starting with 8, and I want to convert step 1, convert to polar. Okay, now you might say, how do I convert that to polar? There's no imaginary part. Well, again, there kind of is. It's just that it's a 0, right? So we're talking about this here, right? So in the imaginary plane here, or in the complex plane, the real part's 8, the imaginary part is 0, right? Or if you like, you could think of this as 8 plus 0i. Okay, so what would your angle here be? Well, you didn't go anywhere, right? Because I mean, you're literally facing where you want it to already face at 0 degrees. And then your r would just be 8, right? You should walk out 8. So in other words, 8 in rectangular would be the same as 8 cis 0 degrees, right? Which should make sense, right? Because what is cosine of 0? 1. 8 times 1 is 8. And what's the sine of 0 degrees? 0. That's why the imaginary part goes away. Okay. Now, again, you could get fancy here, and you could use negative 8. It's just that if you use negative 8, then you would have to use 180 degrees, right? Because now you would be rotating and going the other way, but then just walk backwards 8, right? So actually, either one of these would work, which again should also make sense, because what's the cosine of 180? Negative 1 times negative 8, positive 8. But what's the sine of 180 degrees? Still 0. That's why the imaginary part goes away. Okay, so I don't know. Most people would probably go with this one because it's easier to work with, but it's up to you. Okay, so first thing you would do is whatever your r is, in this case, the number out front, you would take the cube. I mean, like if we're going to use this one, so basically what I'm looking for is I want to find all cube roots of 8 cis 0 degrees. Okay, so the first thing you would do is you take your 8 and you would do the normal number that you're used to is 2. Okay, now what you'd want to do is take your angle and break it into 2 pieces. Okay, you want to think of it as your start, and then think of it as kind of like that pieces idea. Remember graphing these things? Whatever, it's kind of like that, but not. So imagine taking your 0 degrees and you would divide by 3. We're dividing by 3 because that's what cube roots I want, right? So in this formula, when they're talking about whatever root they're looking for, that's the end they're talking about here, right? So you take your starting angle, whatever it is, and divide by 3. Then take a full rotation and divide by 3. right? So think of it as what you're doing ultimately is, I mean, this one, I mean, if you take 0 and divide by 3, you're still going to get 0, which is this, right? And then 360 divided by 3, obviously, well, would be 120. So what I'm saying is, if this is my first one, then you add 120 would get me to here. Then I would add 120 that would get me to here. And then added 120 basically fills in, right? So we're taking the unit circle or trip all the way around and we're breaking it into 3 pieces. Why 3 pieces? Cube roots, right? So you take your beginning angle, that's your starting point, and then take and break the rest of it into 3 pieces, okay? So basically what you would do then is think of it as it's going to be 2 cis 0 degrees, then 2 cis 120 degrees, then 2 cis add another 120, right? So think of this is 0, 120, and add another 120 would be 240, right? And you should probably check, but if I add another 120, that would indeed get me back to where I started, right? 360. Okay, so really, there's your answers, right? Those are them. Okay. Now you could leave it like that, but since we started, we're talking about 8 in rectangular form, we probably want to switch back to rectangular form, right? So you could think of this as 2 cosine 0 degrees plus I sine 0 degrees, right? But sine of 0 again is 0, so this goes away. Cosine of 0 is 1, so this is indeed 2. But that's the one we knew already, okay? One of the cube roots of 8 is definitely 2. Right? These are the other 2 that we've been looking for that we couldn't find any other way, but now we have a way, right? So now what we're talking about is the cosine of 120 degrees plus I sine of 120 degrees, right? Let's do it over here. Well, okay, so I need the cosine of 120 degrees. So that's this one here, right? So the reference angle here would be 60 degrees, right? Because it's 60 degrees short of 180. Okay, so the cosine of 60 degrees, that's the larger angle, so then cosine would be the smaller one, which is the half, and then the sine would be the root 3 over 2, right? But since we're in quadrant 2, we went to the left, and we went up, positive, right? So the cosine would be negative, and the sine would be positive. Or in other words, when you distribute the 2, we're looking at negative 1 plus I root 3. All right, so there's actually another one. And then this one, cosine of 240, do the same thing, would be the 2 cosine of 240 plus I sine of 240. Or again, 240 here, the reference angle is going to be the same thing, right? It's still going to be 60 degrees, so this is still going to be a half, and this is still going to be root 3 over 2, right? The only difference now is you're in quadrant 3. So if you're in quadrant 3, it would go to the left and down. Or in other words, when you distribute the 2, you're now left with negative 1 minus I root 3, right? So these 3 would be your answers, right? So all 3 of these numbers would be cube roots of 8. Okay, or you can check. I mean, if I take 2 and cube it, see, look, it gives me 8. Okay, if you were to take this number in parentheses, negative 1 plus I root 3, no, I. Oh my God. I root 3. There we go. So that whole number, negative 1 plus I root 3, and if I raise it to the third power, sure enough, it gives me 8 as well. Right? And you could do the same thing, the other one, negative 1 minus I root 3. And raise that to the third power, sure enough, it gives you 8 as well. So the 3 numbers that if you cubed or multiplied by itself 3 times, that would give you 8 are 2, negative 1 plus I root 3, and negative 1 minus I root 3. Okay, let's try a different one. I think this is really where it's useful because, again, we're starting with a real number, and without doing this whole cis thing, you would never get to these crazy imaginary. I mean, there's other ways to do it, but honestly, this is the quickest way to do it. Okay, this is, that's really why this is useful. But just to see how this process works, let's try a different one. Let's say I wanted to find the 5th roots of something like 32 cis 5 pi over 3. Okay, so I mean, you can play around with this crazy formula if you like, right? But think of it as, in this case, n is 5. it's already in polar form, right? So basically, you would the first one or the initial one here, your whatever is you look at this the r out front here. So you were talking about the fifth root of 32, like the normal root. This is the one the calculator would give you, right? You could throw that in the calculator to see what the fifth root of 32 is, right? But what you're looking for is what number times itself times itself times itself times itself is 32, which turns out to be 2, right? Again, how could I do that in the calculator? A couple different ways. You could do 5, and then if you go to the math, there actually is an X root button, but you got to type the number in first so that it'll plug 5 into it for you, right? Or depending on which calculator you have, sometimes you call that up and there'll be a little blank and you can move the cursor up there, right? Whatever. But it's the fifth root of 32. Or you could do 32 raised to the 1/5, right? And whatever the index is, that's your denominator, right? Whatever root you're looking for, that's really the denominator of your power. But either way, again, that's the real one, right? That's the one your calculator is going to give you. But there are 4 other ones, right? Because there's 5 answers here. There's 4 other ones that the calculators are not, okay? So how you get to those, think of it as you have a start, and then you would have a piece, okay? So my start here is you would take the 5 pi over 3 and divide by how many roots you want, which in this case is 5. So when you do that, you're going to get pi over 3. So that's where you're starting. Then think of your piece. So the whole all the way around, since we're in radians, we're talking about 2 pi, and you would divide that by 5. All right, now that you can't simplify, so that's your piece. So think of it as you're going to start here and keep adding this over and over and over again until I find all 5 of them, basically. Right? Okay, so one thing you could do is you say, okay, I want to start with pi over 3. There's the first one. Then take pi over 3 and add my next piece, which is 2 pi over 5. But you know you got to get a crazy common denominator here, right? So you might want to think of this pi over 3, and this 2 pi over 5 is something over 15. So multiply top and bottom by 5 here. This would be 5 pi over 15. Multiply top and bottom by 3. This would be 6 pi over 15, right? So this is really 11 pi over 15. Okay. Then you would take that answer, 11 pi over 15, and add another piece. But I want to add 2 pi over 5. But I've already switched it, so let's just go to 6 pi over 15, right? You see what I'm doing though? So basically, you're starting with this, and then you just keep adding this piece until you find all 5 of them, right? So there's my starting value. Add the next one, right? And then add the next one again. But again, just it's already common denominator here, so this would be 17 pi over 15. Then take 17 pi over 15, and add another 16 pi over 15. So this is now 23 pi over 15. And then take 23 pi over 15 and add 6 pi over 15, right? Which would now get you to 29 pi over 15. And then you say, okay, so basically you keep adding this piece. How do you know when to stop? Well, you've got 1, 2, 3, 4, 5 of them. You are done. Or you could keep going. 29 pi over 15 plus the 6 pi over 15. If you did that, this would give you 35 pi over 15. Okay, and one thing that you probably should note there is, what the heck is that? 35 pi over 15. Well, think about that. I mean, one thing you could do is get rid of a 5 here. So if I get rid of a 5 here, this would convert this back to a 3, and this would convert this to 7 pi over 3. Right? Think about 7 pi over 3. Where are you at? Right? This is the same as 6 pi over 3 plus pi over 3. Right? Or in other words, where is this? This is right back to where you started, right? 7 pi over 3 would terminate at the same spot as pi over 3, right? So that's the other way you could do it, is just keep adding until you get to one that gets me right back to where I started. And you've already got this one, so I don't need this one. There's my 5, right? So those are my angles. Now I got to write the actual answer, right? So what are my answers here? Are basically, they're all going to be 2 cis whatever. So it's 2 cis pi over 3. Right? Then again, it would be 2 cis. Add the next one, which was 11 pi over 15. And then 2 cis 17 pi over 15. 23 pi over 15. And then 29 pi over 15. Right? Those are your 1, 2, 3, 4, 5 roots. Okay. It's kind of hard to check these, right? But you could. What I mean by that is, well, where did this one come from? It came from here, Where did this one come from? Came from here. Where did this one come from? Came from here. Where did this one come from? It came from here. So what I'm saying is, if we check that very last one and it works and it came from the other ones, then the other ones are probably right as well, right? So instead, I mean, you could sit there and check them all, right? But since each one of those build on top of each other, if I check the last one and it works, most likely the rest of them work. So how would I check that? Well, what you could do, you're trying to see, it's a lot of typing, but we're trying to see if this is a fifth root of that. Or in other words, this raised to the fifth power should get me back to here, right? So you can check that, right? Now, again, the calculator is going to automatically switch everything to back to rectangular. So you can type 2 cosine of, oh no, I got to make sure you switch the ratings, right? So 2 cosine of the 29 pi divided by 15, right? Plus then the I sine 29 pi divided by 15. Those close, right? So cosine 29 pi over 15, so I sine 29 pi over 15. All right, so that's my number. There it is. Now what I'm checking is I want to raise that to the fifth power. Okay, that's some crazy decimal, but I want to check to see if that's the same as that. Okay, so now if I plug that in the calculator, 32 times cosine of, no, 5 pi divided by 3 plus I sine 5 pi divided by 3. Right? So this number is 32 cosine 5 pi over 3 plus I sine of 5 pi over 3. Okay? And so the point is I took my answer, raised it to the fifth power, gave me this in rectangular. So the number I started with in rectangular, same number. So I'm good to go. Right? Now again, that's only one of them. You would technically probably should check the other ones, but again, if the last one works, the other ones all probably do as well. Okay. So ultimately, here's the point. Let's say I wanted to find all solutions of the following equation. And again, this might be mixed up in, I mean, again, all these are different tools you might need later, right? So in some other context, you know, when you're trying to do something, maybe you're trying to solve the equation x to the 6 plus 1 equals 0. And you may look at this and you may not even be thinking imaginary in any way, shape, or form, right? How would I solve this? Well, knowing that there are 6 different answers here. Okay, so how would I do this? One thing you could do is think of it as, oh, I want x to the 6 to be equal to -1. Or in other words, what are we trying to do? We are trying to find all 6 roots of -1. Right? So we're trying to find 6 different answers here. So that when I multiply by themselves 6 times, it does give me -1. Okay, so how do I do this? Step 1, take -1 and convert. And one thing you could do is you could use the 6th root, and again, that'd be the 6th root of -1. So you're probably thinking, hey, there's an I involved here somewhere, right? Because you got a root with a negative, well, not just root, but an even root with a negative underneath it. It's probably an I floating around. Okay, this is how we find them, right? So let's convert -1 to polar. So again, maybe a picture would help here, but it's -1, meaning you're going to go back 1, and for starters, there is no imaginary, so you're not going up or down, so it's just there. Or you could think of this as my angle is 180 degrees, and then just walk forward 1, okay? Or you could use 0 and then walk backwards 1. It's up to you, okay? So you could think of -1 as basically, probably the easiest would be 1 cis 180 degrees, right? This way would be easier because now I don't have to deal with that negative for my r, right? Because if you did it the other way, I mean, -1 equals -1 cis 0 degrees, which is true. You still got to find the 6th root of that, which is what we're after. That's not helpful, right? So what I mean by that is I need to find the 6th root of this using this one and not this one, okay? I need the 6th root of my r out front. So the 6th root of 1, oh, the nice one that the calculator would give me is just 1, okay? Now I got to find my angles. So think of it as my start, and then think of it as your pieces. Okay, so where am I starting at? If I use this one, you're starting at 180, and I would divide that by 6. And then my pieces take the whole circle every time and divide by 6. So in this case, I'm starting at 30 degrees, and then you would add 60 degrees, right? So literally, at this stage, you probably could write them all out. What I mean by that is it's going to be, they're all going to be the same. 1, 1, 2, 3, 4, 5, 6. Cis, cis, cis. Right? So my starting one is going to be 30 degrees. Then you would just keep adding 60 degrees. So this would be 90, 150, 210, 270, and then 330. And again, you Oh, and then you keep going, because if I added another 60, right, that would give me 390, but that's 30 more than 360. I'm right back to where I started. I'm good to go, right? So there they are. Well, we could convert these all to rectangular then. I mean, there's R is 1, so I really don't need that. So all I really need here is the cosine of 30 degrees, right? So the cosine of 30 degrees is the root 3 over 2 plus the 1/2 I, right? The sine is 1/2. Then 90 degrees, think about 90 degrees. Cosine of 90 degrees is 0. Sine of 90 degrees is 1. So basically this is just going to be I. 150 degrees, again, it's 30 degrees short. So I mean, all of these have the same reference handle. They're all 30 degrees, right? Because this is 30 degrees short of 180, right? So this is still going to be root 3 over 2, right? This is still going to be 1/2 I. But now it's in quadrant 2, which means it went to the left and up, right? 210, that's 30 degrees more than 180, so it's still going to be root 3 over 2. It's still going to be the 1/2 I. But now you're in quadrant 3, so left and down. And then 270, that's straight down, right? So that means now the cosine is 0, and the sine would be -1. So basically, this is just negative I. And then 330 is 30 degrees short of going all the way around, so this is still root 3 over 2. This is still 1/2. But now you're in quadrant 4, so you went to the right and down. And there we go. And there's, again, all 6 of these. And you can check it out, right? I mean, like, what I mean by that is you can plug them back in if you want it, right? So think of, well, in parentheses, turn it on first off. In parentheses, if you did the root 3, right, divided by 2, plus the 1/2, or 0.5, just because I'm lazy. It's easier to type that in. I, right? So root 3 over 2 plus 1/2 I, raise it to the 6th power, right? Okay, now you might say, oh, that didn't give me, yes, it did. Because look, it's supposed to be -1. So here's the real part is -1. Plus, it gave me this 1e to the -13. What the heck is that? That's 0.001, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, right? This is scientific notation. So basically what's happening here, calculators are dumb. It's just doing dumb things really fast, right? It's using approximations for these things. So we got really close, but it's pretty much 0, which means this is not there. It is, in fact, just -1, right? So it does work. And then you could do I to the 6, right? Let me get rid of this. I raised to the 6th power. That one indeed gives you -1, just for laziness. The next one I want to type in is a negative root 3, so we can go back and just make that negative. Sure enough, that one gives me -1, and then you can do the negative I, right? But if you do negative I raised to the 6th power, don't do this, right? Because this won't work, right? Make sure you put in parentheses, it's negative I raised to the 6th. Now it works, right? So on and so on. You can check out the rest, but they all do work, okay? Last one. This one's actually easier, or at least it's quicker. All right, so let's say I wanted to solve this equation, right? So it's kind of the same thing. You could say, okay, I could solve for the x part, right? So think of this x to the 4th is 8 divided by 2. So then the x to the 4th would be 4. Or in other words, we're trying to find all 4th roots of 4. Okay, so the nice one, it's not really nice in this context, but the one that the calculator is going to give you, you want the 4th root of 4, or 4 to the 1/4, right? Which it's not a nice number, right? Because it's 4 raised to the 1/4, right? Which is not going to be a nice number, right? So I mean, you could just leave it like that, the 4th root of 4, okay, or use the decimal, right? Pay attention to the directions. If it says exact, leave this. If it says approximate, then you can approximate. Okay. Then as far as my angles, I need to start. Oh, no, I didn't convert it yet. Sorry. But, okay, this is easy to convert, hopefully, right? It's 4, right? So it's over here, right? So in rectangular is 4. So then what's my angle here is just 0 degrees and walk out 4, right? So it's 4 cis 0, which is why you're getting this. Okay, so now my start is 0 degrees divided by 4. And then the pieces, you would do the 360 divided by 4. Right? So you'd start at 0, and then you would keep adding 90 degrees. Okay, so you're going to have 4 answers here. All 4 of them are going to look like this. You would just start at 0 degrees, add 90, add 90, add 90. And you could add 90 again, but when you add 90 again, you're going to be right back to 360, which is back to the same one. So there you go. At least in polar form. Then if you wanted to, you could switch back to rectangular form, right? So basically this is the fourth root of 4, right? The cosine of 0 is 1, and then the sine of 0 is 0, right? So basically this is the fourth root of 4, right? That's the nice one, okay? Then we want the fourth root of 4. Cosine of 90 degrees is 0, plus the sine of 90 degrees is 1, right? So this would basically be I times the fourth root of 4. And then we want the fourth root of 4 times cosine of 180, right? That's to the left, so that'd be negative 1, and then the sine is 0, right? So basically this would be negative fourth root of 4. And then the fourth root of 4, last one here, cosine of 270 would be the 0, but the sine is negative 1. So basically this would be negative I, fourth root of 4. So in rectangular form, there you go. Which again, you could check. I mean, one thing you could do is plug it. I mean, we're trying to ultimately solve this equation, so it's really 2 times some number raised to the 4th, right? So you can type the whole thing in 2, and then I want 4 raised to the 1/4. I gotta put that in parentheses, right? So there's my x. I want that raised to the 4th power minus 8, right? Does indeed give you 0, right? So plugging in 4 to the 1/4, 2x to the 4th minus 8. Right? Or you could take that same thing and then insert an I, still gives me 0. Whoops. You could take that same thing, but just make it negative instead of an I, or actually I do negative, not minus. Still gives you 0. And you could do the same thing for you did negative, oh no, not. I, right? So negative I, plugging that in, still gives you 0. All 4 of those do indeed work. Right? So it's kind of crazy how that works, right? But just some other stuff that you could do with these complex numbers, especially in polar form.